Okay, and the second innovation that is very helpful for optimizing very deep neural networks is right here. So we have this addition now, that's the residual part. But this norm is referring to something called layer norm. So layer norm is implemented in PyTorch. It's a paper that came out a while back here. And layer norm is very, very similar to bash norm. So remember back to our Make More series part 3. We implemented bash normalization. And bash normalization basically just made sure that across the bash dimension, any individual neuron had unit Gaussian distribution. So it was 0 mean and unit standard deviation, 1 standard deviation output. So what I did here is I'm copy pasting the bash norm 1D that we developed in our Make More series. And see here we can initialize, for example, this module, and we can have a batch of 32 100-dimensional vectors feeding through the bash norm layer. So what this does is it guarantees that when we look at just the 0th column, it's a 0 mean, 1 standard deviation. So it's normalizing every single column of this input. Now the rows are not going to be normalized by default because we're just normalizing columns. So let's now implement layer norm. It's very complicated. Look, we come here, we change this from 0 to 1. So we don't normalize the columns, we normalize the rows. And now we've implemented layer norm. So now the columns are not going to be normalized, but the rows are going to be normalized. For every individual example, its 100-dimensional vector is normalized in this way. And because our computation now does not span across examples, we can delete all of this buffers stuff because we can always apply this operation and don't need to maintain any running buffers. So we don't need the buffers. There's no distinction between training and test time. And we don't need these running buffers. We do keep gamma and beta. We don't need the momentum. We don't care if it's training or not. And this is now a layer norm. And it normalizes the rows instead of the columns. And this here is identical to basically this here. So let's now implement layer norm in our transformer. Before I incorporate the layer norm, I just wanted to note that, as I said, very few details about the transformer have changed in the last 5 years, but this is actually something that slightly departs from the original paper. You see that the add and norm is applied after the transformation. Now it is a bit more basically common to apply the layer norm before the transformation. So there's a reshuffling of the layer norms. So this is called the pre-norm formulation, and that's the one that we're going to implement as well. So slight deviation from the original paper. Basically, we need two layer norms. Layer norm 1 is nn.layer norm, and we tell it how many, what is the embedding dimension. And we need the second layer norm. And then here, the layer norms are applied immediately on X. So self.layer norm 1 applied on X, and self.layer norm 2 applied on X before it goes into self-attention and feed forward. And the size of the layer norm here is an embed, so 32. So when the layer norm is normalizing our features, it is the normalization here happens, the mean and the variance are taken over 32 numbers. So the batch and the time act as batch dimensions, both of them. So this is kind of like a per token transformation that just normalizes the features and makes them unit mean, unit Gaussian at initialization. But of course, because these layer norms inside it have these gamma and beta trainable parameters, the layer norm will eventually create outputs that might not be unit Gaussian, but the optimization will determine that. So for now, this is incorporating the layer norms, and let's train them on. Okay, so I let it run, and we see that we get down to 2.06, which is better than the previous 2.08. So a slight improvement by adding the layer norms. And I'd expect that they help even more if we had a bigger and deeper network. One more thing I forgot to add is that there should be a layer norm here also typically as at the end of the transformer and right before the final linear layer that decodes into vocabulary. So I added that as well. So at this stage, we actually have a pretty complete transformer according to the original paper, and it's a decoder-only transformer. I'll talk about that in a second. But at this stage, the major pieces are in place, so we can try to scale this up and see how well we can push this number. Now, in order to scale out the model, I had to perform some cosmetic changes here to make it nicer. So I introduced this variable called nLayer, which just specifies how many layers of the blocks we're going to have. I create a bunch of blocks, and we have a new variable, number of heads as well. I pulled out the layer norm here, and so this is identical. Now, one thing that I did briefly change is I added dropout. So dropout is something that you can add right before the residual connection back, or right before the connection back into the residual pathway. So we can drop out that as the last layer here. We can drop out here at the end of the multi-headed extension as well. And we can also drop out here when we calculate the basically affinities, and after the softmax, we can drop out some of those. So we can randomly prevent some of the nodes from communicating. And so dropout comes from this paper from 2014 or so. And basically it takes your neural net and it randomly, every forward-backward pass, shuts off some subset of neurons. So randomly drops them to 0 and trains without them. And what this does effectively is, because the mask of what's being dropped out is changed every single forward-backward pass, it ends up kind of training an ensemble of subnetworks. And then at test time, everything is fully enabled and kind of all of those subnetworks are merged into a single ensemble, if you want to think about it that way. So I would read the paper to get the full detail. For now, we're just going to stay on the level of this is a regularization technique, and I added it because I'm about to scale up the model quite a bit, and I was concerned about overfitting. So now when we scroll up to the top, we'll see that I changed a number of hyperparameters here about our neural net. So I made the batch size be much larger, now it's 64. I changed the block size to be 256. So previously it was just 8 characters of context. Now it is 256 characters of context to predict the 257th. I brought down the learning rate a little bit because the neural net is now much bigger, so I brought down the learning rate. The embedding dimension is now 384, and there are 6 heads. So 384 divided 6 means that every head is 64 dimensional as a standard. And then there are going to be 6 layers of that. And the dropout will be at 0.2. So every forward-backward pass, 20% of all of these intermediate calculations are disabled and dropped to 0. And then I already trained this and I ran it. So drum roll, how well does it perform? So let me just scroll up here. We get a validation loss of 1.48, which is actually quite a bit of an improvement on what we had before, which I think was 2.07. So we went from 2.07 all the way down to 1.48 just by scaling up this neural net with the code that we have. And this, of course, ran for a lot longer. This maybe trained for, I want to say, about 15 minutes on my A100 GPU. So that's a pretty good GPU. And if you don't have a GPU, you're not going to be able to reproduce this. On a CPU, this would be, I would not run this on a CPU or a MacBook or something like that. You'll have to bring down the number of layers and the embedding dimension and so on. But in about 15 minutes, we can get this kind of a result. And I'm printing some of the Shakespeare here, but what I did also is I printed 10,000 characters, so a lot more, and I wrote them to a file. And so here we see some of the outputs. So it's a lot more recognizable as the input text file. So the input text file, just for reference, looked like this. So there's always like someone speaking in this manner. And our predictions now take on that form, except of course they're nonsensical when you actually read them. So it is, every crimpty be a house. Oh, those preparation, we give heed. You know, oh ho, sent me you mighty Lord. Anyway, so you can read through this. It's nonsensical, of course, but this is just a transformer trained on the character level for 1 million characters that come from Shakespeare. So it's sort of like blabbers on in Shakespeare-like manner, but it doesn't, of course, make sense at this scale. But I think still a pretty good demonstration of what's possible. So now I think that kind of like concludes the programming section of this video. We basically kind of did a pretty good job in, of implementing this transformer. But the picture doesn't exactly match up to what we've done. So what's going on with all these additional parts here? So let me finish explaining this architecture and why it looks so funky. Basically what's happening here is, what we implemented here is a decoder-only transformer. So there's no component here. This part is called the encoder, and there's no cross-attention block here. Our block only has a self-attention and the feed-forward. So it is missing this third in-between piece here. This piece does cross-attention. So we don't have it, and we don't have the encoder. We just have the decoder. And the reason we have a decoder only is because we are just generating text, and it's unconditioned on anything. We're just blabbering on according to a given data set. What makes it a decoder is that we are using the triangular mask in our transformer. So it has this autoregressive property where we can just go and sample from it. So the fact that it's using the triangular mask to mask out the attention makes it a decoder, and it can be used for language modeling. Now, the reason that the original paper had an encoder-decoder architecture is because it is a machine translation paper. So it is concerned with a different setting. In particular, it expects some tokens that encode, say, for example, French, and then it is expected to decode the translation in English. So you typically, these here are special tokens. So you are expected to read in this and condition on it. And then you start off the generation with a special token called start. So this is a special new token that you introduce and always place in the beginning. And then the network is expected to output neural networks are awesome, and then a special end token to finish the generation. So this part here will be decoded exactly as we've done it. Neural networks are awesome will be identical to what we did. But unlike what we did, they want to condition the generation on some additional information. And in that case, this additional information is the French sentence that they should be translating. So what they do now is they bring in the encoder. Now the encoder reads this part here. So we're only going to take the part of French, and we're going to create tokens from it exactly as we've seen in our video. And we're going to put a transformer on it. But there's going to be no triangular mask. And so all the tokens are allowed to talk to each other as much as they want. And they're just encoding whatever's the content of this French sentence. Once they've encoded it, they basically come out in the top here. And then what happens here is in our decoder, which does the language modeling, there's an additional connection here to the outputs of the encoder. And that is brought in through cross-attention. So the queries are still generated from X, but now the keys and the values are coming from the side. The keys and the values are coming from the top, generated by the nodes that came outside of the encoder. And those tops, the keys and the values there, the top of it, feed in on a side into every single block of the decoder. And so that's why there's an additional cross-attention. And really what it's doing is it's conditioning the decoding, not just on the past of this current decoding, but also on having seen the fully encoded French prompt, sort of. And so it's an encoder-decoder model, which is why we have those two transformers, an additional block, and so on. So we did not do this because we have nothing to encode. There's no conditioning. We just have a text file, and we just want to imitate it. And that's why we are using a decoder-only transformer, exactly as done in GPT. Okay, so now I wanted to do a very brief walkthrough of NanoGPT, which you can find on my GitHub. And NanoGPT is basically two files of interest. There's train.py and model.py. Train.py is all the boilerplate code for training the network. It is basically all the stuff that we had here. It's the training loop. It's just that it's a lot more complicated because we're saving and loading checkpoints and pre-trained weights, and we are decaying the learning rate and compiling the model and using distributed training across multiple nodes or GPUs. So the training.py gets a little bit more hairy, complicated. There's more options, etc. But the model.py should look very, very similar to what we've done here. In fact, the model is almost identical. So first, here we have the causal self-attention block, and all of this should look very, very recognizable to you. We're producing queries, keys, values, we're doing dot products, we're masking, applying softmax, optionally dropping out, and here we are pooling the values. What is different here is that in our code, I have separated out the multi-headed attention into just a single individual head, and then here I have multiple heads and I explicitly concatenate them. Whereas here, all of it is implemented in a batched manner inside a single causal self-attention. And so we don't just have a B and a T and a C dimension, we also end up with a fourth dimension, which is the heads And so it just gets a lot more sort of hairy because we have 4-dimensional array tensors now, but it is equivalent mathematically. So the exact same thing is happening as what we have. It's just it's a bit more efficient because all the heads are now treated as a batch dimension as well. Then we have the multilayer perceptron. It's using the Gelu nonlinearity, which is defined here instead of ReLU. And this is done just because OpenAI used it, and I want to be able to load their checkpoints. The blocks of the transformer are identical, the communicate and the compute phase, as we saw. And then the GPT will be identical. We have the position encodings, token encodings, the blocks, the layer norm at the end, the final linear layer. And this should look all very recognizable. And there's a bit more here because I'm loading checkpoints and stuff like that. I'm separating out the parameters into those that should be weight decayed and those that shouldn't. But the generate function should also be very, very similar. So a few details are different, but you should definitely be able to look at this file and be able to understand a lot of the pieces now. So let's now bring things back to ChatGPT. What would it look like if we wanted to train ChatGPT ourselves, and how does it relate to what we learned today? Well, to train in ChatGPT, there are roughly 2 stages. First is the pre-training stage, and then the fine-tuning stage. In the pre-training stage, we are training on a large chunk of internet and just trying to get a first decoder-only transformer to babble text. So it's very, very similar to what we've done ourselves, except we've done like a tiny little baby pre-training step. And so in our case, this is how you print a number of parameters. I printed it and it's about 10 million. So this transformer that I created here to create a little Shakespeare transformer was about 10 million parameters. Our data set is roughly 1 million characters, so roughly 1 million tokens. But you have to remember that OpenAI uses different vocabulary. They're not on the character level. They use these subword chunks of words. And so they have a vocabulary of 50,000, roughly, elements. And so their sequences are a bit more condensed. So our data set, the Shakespeare data set, would be probably around 300,000 tokens in the OpenAI vocabulary, roughly. So we trained about 10 million parameter model on roughly 300,000 tokens. Now, when you go to the GPT-3 paper and you look at the transformers that they trained a number of transformers of different sizes, but the biggest transformer here has 175 billion parameters. So ours is, again, 10 million. They used this number of layers in the transformer. This is the N embed. This is the number of heads. And this is the head size. And then this is the batch size. So ours was 65. And the learning rate is similar. Now, when they trained this transformer, they trained on 300 billion tokens. So again, remember, ours is about 300,000. So this is about a million-fold increase. And this number would not be even that large by today's standards. You'd be going up 1 trillion and above. So they are training a significantly larger model on a good chunk of the internet. And that is the pre-training stage. But otherwise, these hyperparameters should be fairly recognizable to you. And the architecture is actually like nearly identical to what we implemented ourselves. But of course, it's a massive infrastructure challenge to train this. You're talking about typically thousands of GPUs having to, talk to each other to train models of this size. So that's just the pre-training stage. Now, after you complete the pre-training stage, you don't get something that responds to your questions with answers and is not helpful and etc. You get a document completer, right? So it babbles, but it doesn't babble Shakespeare, it babbles internet. It will create arbitrary news articles and documents, and it will try to complete documents because that's what it's trained for. It's trying to complete the sequence. So when you give it a question, it would just potentially just give you more questions. It would follow with more questions. It will do whatever it looks like some closed document would do in the training data on the internet. And so who knows, you're getting kind of like undefined behavior. It might basically answer with 2 questions with other questions. It might ignore your question. It might just try to complete some news article. It's totally unaligned, as we say. So the second fine-tuning stage is to actually align it to be an assistant. And this is the second stage. And so this ChatGPT blog post from OpenAI talks a little bit about how this stage is achieved. We basically, there's roughly 3 steps to this stage. So what they do here is they start to collect training data that looks specifically like what an assistant would do. So they are documents that have the format where the question is on top and then an answer is below. and they have a large number of these, but probably not on the order of the internet. This is probably on the order of maybe thousands of examples. And so they then fine-tune the model to basically only focus on documents that look like that. And so you're starting to slowly align it. So it's going to expect a question at the top, and it's going to expect to complete the answer. And these very, very large models are very sample efficient during their fine-tuning. So this actually somewhat works. But that's just step one. That's just fine-tuning. So then they actually have more steps where, okay, the second step is you let the model respond, and then different raters look at the different responses and rank them for their preference as to which one is better than the other. They use that to train a reward model. So they can predict, basically using a different network, how much of any candidate response would be desirable. And then once they have a reward model, they run PPO, which is a form of policy gradient reinforcement learning optimizer, to fine-tune this sampling policy so that the answers that ChatGPT now generates are expected to score a high reward according to the reward model. And so basically there's a whole aligning stage here, or fine-tuning stage. It's got multiple steps in between there as well. And it takes the model from being a document completer to a question answerer. And that's like a whole separate stage. A lot of this data is not available publicly. It is internal to OpenAI, and it's much harder to replicate this stage. And so that's roughly what would give you a ChatGPT. And NanoGPT focuses on the pre-training stage. Okay, and that's everything that I wanted to cover today. So we trained, to summarize, a decoder-only transformer following this famous paper, Attention is All You Need, from 2017. And so that's basically a GPT. We trained it on a tiny Shakespeare and got sensible results. All of the training code is roughly 200 lines of code. I will be releasing this code base. So also it comes with all the git log commits along the way as we built it up. In addition to this code, I'm going to release the notebook, of course, the Google Colab. And I hope that gave you a sense for how you can train these models like, say, GPT-3 that will be architecturally basically identical to what we have, but they are somewhere between 10,000 and 1 million times bigger, depending on how you count. And so that's all I have for now. We did not talk about any of the fine-tuning stages that would typically go on top of this. So if you're interested in something that's not just language modeling, but you actually want to, say perform tasks, or you want them to be aligned in a specific way, or you want to detect sentiment or anything like that. Basically, anytime you don't want something that's just a document completer, you have to complete further stages of fine-tuning, which we did not cover. And that could be simple supervised fine-tuning, or it can be something more fancy like we see in ChatGPT, where you actually train a reward model and then do rounds of PPO to align it with respect to the reward model. So there's a lot more that can be done on top of it. I think for now we're starting to get to about 2 hours mark, so I'm going to kind of finish here. I hope you enjoyed the lecture, and yeah, go forth and transform. See you later.